Hey, workshop students, I got a question about your yo-yo problem. So I'm going to work on it here now. Might be a little bit on the late side, and I apologize for that, but let me work through it nonetheless. It says a yo-yo is a disc that has a mass of 104 grams, so m equals 104 grams, although I'm going to put that as 0.104 kilograms. Okay, and has a radius of, it looks like your author calls this an r sub y, okay? Radius of 3.17 centimeters. Maybe I'll put that as 0.0307 meters in case I want to do things in meters. Probably do. It says the string is wrapped around an inner spool, which has a very small mass. So we can neglect the mass of the string. The radius and a radius of, and so the string is wrapped around something like this. So here's the tension in the string. Actually, you'd see your picture calls it F sub S for the force in the string, I'm sure. And then this is an R sub S, radius of the string, and it's 1.02 centimeters, which I'll write as 0.0102 meters. Okay. Vandam holds on to the string and lets the yo-yo fall straight down with an acceleration of a. And so it's going to be falling and unwinding here, okay? And there's really two ways to look at this problem. One of the ways to do it is to look at the rotation around its center of mass, okay? Another way would be to look maybe at it's pivoting at an instant around the connection of the string as it kind of tumbles down. Maybe we should do both, but I think it's probably a little bit easier to see, but harder mathematically, to do the first case. So let's talk about it as it rotates around the string. But this fits into what I had shared with you guys early on in the semester, these 4 steps. And I'll say them again. The first step is get a good physical picture of what's going on. Number 2, draw the free body diagram. Number 3, write out the equations using Newton's second law. And in this case, what's new here is this will be in Newton's second law, one of translation and one of rotation, and then solve. But it's still those 4 steps. So I'm working here on step number 1. Do you got a good physical picture of what's going on? Do you see here that you have a yo-yo? And that yo-yo is going to be moving down and unwinding as it moves down. And it unwinds off of this string. So there's a force on that string. Now, let me not continue to draw the forces because that's step 2 where we do the free body diagram. But I just want to make sure that I've accomplished step number 1, and that is, do I have a good physical picture of what's going on? And I think so. I think I understand that gravity is going to be tugging down on it, okay, by its center of mass, mg. Okay, the string's going to be tugging up on it. Those two would be a little different, resulting in it going down. And so it's going to have an acceleration downward. So the mg must be a little bit greater than the force from the spring. That's why it's accelerating. And that as it goes down, that's a translational motion. But at the same time, it unwinds, and so it has a rotational motion. So it has both translation and rotation. Okay, but one step at a time. So step 1, good physical picture. I think I got that. Step 2, free body diagram. Free body diagram says draw the diagram, okay, so I have here, and then draw all the forces, which includes gravity and everything touching it. And in my conversation, I think I'm there. Here's the force of gravity. It's at the center of mass, okay? And then there is the only thing touching it, which is the string, which is pulling upward. and it is off-centered by this radius of the string, this 1.02 centimeters. Okay, so I think I got the free body diagram. So now I can go on to write out my equations. And maybe I'll just make kind of a 2-axis, because one set of equations will be for the translational motion and the other will be for the rotational motion. The translational motion says the sum of all the forces equals ma. And it could even move x and y, but this problem is only in the y direction, so I'll just put a sub y and drop the arrowheads. And so my first equation would be, and it depends how you want to do this, if you want to call, say, down positive, you can, or maybe be better to stick to the tradition. Maybe, I'll stick to the traditional way. So, no, yeah, okay. I'll leave the tradition. I'm going to call down positive. Okay, so when I add up all the forces, mg is down and the force from the string is up. And so that's why it's a minus sign. So there's the sum of all the forces. And that has to equal to ma. And that's what I'm looking for, the A. And of course, I don't know the force from the string. I do know the mass and I do know g. So there's two unknowns right here. So this by itself, I can't go anywhere. That's why, again, step 3 is write out the equations. And so this is that equation. Okay. Now, over here, I'll do the rotation. And this says the sum of all the torques is equal to I alpha. Okay, now, again, torques would depend upon what axis you are going to rotate in your mind about. And maybe the best axis, and I'll do a different color here, is to pick the center. And the reason that's important is because torque is this RF sine of the angle between R and F. And so when you look at all the torques, particularly the torque that comes from the mg, you would say, okay, well, the force is mg, but the R is 0. There is 0 distance between where the force is acting and its pivot point. Because the force is acting at its center of mass, and that is its pivot point. That is how we're calculating. We're calculating the torque about its pivot point. Okay. So with that in mind, then that would make the R equals to 0. So the force of gravity is not giving me any torque, at least if I pick that point. Now remember, just like we could pick up or down any point, we could pick the pivot point to be anyone. And I'll show you in a little bit after we do this problem to redo it, and we'll do the pivot point right here. But as stated, if I pick the pivot point to be the center of mass here, I get 0 torque from gravity. What I do get then is a torque from the string. So it would be the force from the string, and the distance away would be RS, and the angle would be 90 degrees. You can kind of see the string pulling up, and that's the neat thing about string is it's flexible, so it'll always unwrap at 90 degrees. And so usually at this point in your semester, everything's kind of 90 degrees. It's with strings. That'll change in the next chapter when we can do tie rods, and we can build a bridge with a tie rod off at some 45-degree angle. So more on that in the next unit here. But for right now, for this particular problem, that's 90 degrees. Now, we should also take a look at what we want to call positive and negative. Now, traditionally, when something gets tugged like this, making it rotate clockwise, we call that negative. And we could stick to that, except it may get us confused with over here. Because remember, we deliberately, or I guess should say, deliberately picked down as positive so the acceleration would be positive. And if we stick to the tradition here, we're going to have a negative angular acceleration. Now, really there's nothing wrong with that, except we also know that translational acceleration equals radius times angular acceleration. So really we should mean magnitude, because we could pick a coordinate system where one is positive and one is negative. And if we call down positive, but we stuck to the traditional clockwise as negative, these would be opposite in sign. So if I want to use this equation with, without the absolute value, I might want to set this up so that a positive translational acceleration also corresponds to a positive angular rotation. Or negative go with negative. And the way this problem is set up, it doesn't always work this way, but with this problem is set up, if you had stuck to the tradition of up being positive, you would then get a negative translational acceleration, but it would also correspond to a negative angular acceleration. So there's not much to think about in this problem if you do that. But there are problems where you're going to get yourself in trouble if you don't think about it. So this one, then, since I already changed the tradition of up positive to down positive, I also, to make it match, I don't have to, but to make it match, otherwise I'd have to do a positive matches a negative, I should call the clockwise a positive. So I'm going to do that. I'm going to call a clockwise rotation positive. So I'm going to go against tradition. So both my translation and my rotation are kind of opposite of tradition. Okay? I could easily have stuck to the same. But as long as I match everything, I'm okay. I can change one or not the other. I can change both. There's all kinds of things I can do. But I do need to be careful between the translation and the rotation when I go to compare them, because this is how I will compare them. And does a positive here match a positive here? Depends how you set it up. Does a negative here match a negative here? Depends how you set it up. Or does a positive here match a negative here? Or negative here with a positive? Yeah, depends how you set it up. Your choice, just pay attention to it. All right, so I'm going to try to set it up so that my translational is positive, which corresponds also to a rotation that is positive. And that's why, once I call down positive, I also would like to, I don't have to, but would like to, call a clockwise positive. So that's what I'm going to do here. So this torque then would be pulling it in a clockwise, which I will call then a positive torque. So I'll say it again. We get no torque from gravity. We get torque only from the string. It is then a positive torque. And that would have to equal to I alpha. But of course, here then is where we get into step 4. And we say, okay, now let's solve this. And you can now see that this equation will come in very handy, because this I can just write as RS FS. Sine of 90 is just 1, so I won't put anything there. The moment of inertia, now again, moment of inertia, like torque, depends what axis are you rotating about. So I had picked from the beginning to rotate it around its center of mass. And so this is a disk. And we know for a disk that it's 1/2 mr squared. Now, let's be careful with our r's, though. This is the radius of the whole disk. So we need to come back here. Remember, the radius of the whole disk was r sub y. Whereas the torque radius is where the force is coming from, and that's the radius of the string. So those are not the same r, which is one of the reasons this can be a harder problem. Okay, now the alpha is related to the translational. So angular and translational are related here. Okay. Now, again, they're related by an R, so let's be careful. Is it RY or is it RS? Well, let's talk for a moment. But that aside, notice that I have an absolute value here. I have to ask myself, do positives match positives? And the answer was yes. I deliberately went through setting it up so that when it was downward for a positive translational rotation, I would have a positive, even though it's clockwise, positive angular rotation. So I can replace this alpha here with just A over R. So this would be A over R. Now here's the question, which R? Well, the R would be, again, this pivot. How fast is it accelerating relative to this pivot? And that is this R sub S. So you can see here that this is a harder problem because we have different R's here. And we have to be careful with that. But once we write it in this fashion, you'll see that we know everything in this equation but the same two that we didn't know here. So now we have our two equations and two unknowns. Or you could have said this was a third unknown, and so this was a third equation. So we had equation 1, equation 2, and equation 3. 3 equations, 3 unknowns. But once I substitute it in, I just like to think of it as now I have one equation and a second equation. Or really, that was the first, so that's the second. So 2 equations, 2 unknowns. So now I can move on to the step 4, which is solve all this math. And since we are, well, maybe I'll do a little more math here on this page, but this can be easily solved for f sub s by putting the 1/2 and the m. I already have an ry squared, and then I divide it by rs squared, because I bring that over, and then an a. And I can put that into this equation, and I'll do that on this next page. So this would be then mg minus 1/2 mry squared over rs squared a equals ma. So then I have an mg, and when I bring this on over, there would be, I'll factor out an a for each term, but there'd be an m here, plus, and then this would be an mry squared on top, and underneath would be a 2rs squared underneath. Now, each has an m, which I can factor out, but it would match this over here. So a would then be a g, and then this would be a 1 plus, and we'd have an ry squared over a 2rs squared. And so now I can put in my numbers and finish the problem. Now, I'll do this first, ry, and I'll just do each of them in centimeters. So this would be 3.07 squared. I would then divide it by a 2, and also divide it by 1.02 squared. And so it looks like this whole number is about a 4.5. Add 1 to it, and that's about a 5. So this would be 9.8 divided by that answer. And so it looks like A comes out to be 1.77 meters per second squared. Yay! And there it is. And of course, didn't ask, but we could go back then and also find the force on the string. But I think it might be a little more enlightening if I just take a little more time and say, could we have done this from a different perspective? Could we have done this back here and picked this as the rotating axis. And absolutely, absolutely we could have. Now, forces have nothing to do with where you put the origin. So if I then want to calculate this problem based upon this rotational axis, the sum of the forces in the y direction equaling ma doesn't change. We'll have the mg going down, we will have the force of the string up, and we will equal ma. So that changing the pivot point, if you will, has nothing to do with forces. Forces are not based upon where the origin is. But torques and moments of inertia do. And so things are going to be a little different, but still going to give you the same answer. So over here, if I were to apply the sum of the torques equal to I alpha, I guess what would come up different right away is I would have to say then that the torque I get from the string would be a zero torque. Because remember, in calculating the torque is the distance from the force to the pivot point. And if I'm putting the pivot point right here where the string is making contact, that's where the string is making contact. There's zero distance between where the string makes contact and where I'm calculating the pivot. And so that R would be zero. And so I would say, in a thinking this way, the torque from the string would be zero, and the torque from gravity would not. So I would get something that would say, all right, zero torque from the string, so I won't even write anything here. But I would say that I get a torque from gravity, and so the force then would be mg. So here's mg. And the distance away would be this r sub s. And so that is different here compared to here, right? Okay, now the other side of the equation, though, would also look different because this would be the rotational inertia. But one of the things that makes rotational problems hard is, as I'm trying to point out, it depends where you pick your pivot. And so if the pivot changes, that changes your R for your torque. And so thinking of it this way, I got an equation that looks surprisingly different. But also, moment of inertia would be different. Because remember, this moment of inertia, which we said was 1/2 mRy squared, is the moment of inertia as measured from the center. And we are doing it off center a little bit. And this is where the parallel axis theorem comes into play, where you take the mass and the distance over from the center. And so this is the moment of inertia of its center, and this is that md squared of the parallel axis theorem. How far over did you move it? So I would say that viewing it this way, we've made maybe calculating the torque easier, but we've made calculating the moment of inertia harder. So I'm not trying to say that this second method is a better one. I'm just trying to say it's different. And then we would have our alpha. Okay. What I really like, though, about this approach is if you look here, we can know everything. We have a 1/2 mRy squared plus an mRs squared. And then right here, if I divide this by A over RS, remember like we said last time, these are related. It's related by S. And then we have this RSMG. You can then really boil this down to just one equation and one unknown. So what is to somewhat of an advantage is if you look at this as the pivot point, you never have to do the translational equation. You only have to do the rotation. In fact, watch. Notice that there would be an m that can be factored out and canceled with that m. Okay. Notice then that, let's see, if I bring, first of all, bring this RS over to here, it becomes squared. And if I then move it inside here, RS squared over RS squared, so we'll get rid of it here, I would have a G on that side. And over here, this would be the plus 1. That would cancel. And then this would be the ry squared over the 2rs squared equals to a. And so you would get a G over, and then this would be 1 plus ry squared over 2rs squared, which is exactly what we got back up here when we calculated it about its center. So that's probably the nice thing about doing it in kind of an off-center. The obnoxious thing is calculating the moment of inertia because you got to go to the parallel axis theorem. But the neat thing about it, and you can see the advantage at the beginning when you gain experience, is it will eliminate this unknown Fs from your equation. Keep that in mind when you get to the next chapter on equilibriums, because sometimes the problem is really got a lot of forces. And sometimes, like, there are 3 unknown forces and 2 of them go to the same point. And if you calculate around that point, the torques from those 2 go away and you're only left with 1 unknown in your equation. And that's what you see here. And that's probably the biggest advantage I can show you. Sometimes it's harder to think that way, but it often makes the equations and calculating the mathematics easier. So whichever works for you. All right, take care.